Okay, good morning. And it's a real pleasure for me to talk to you about Atlas. The Atlas talks will be in two parts. I will cover in the first part what is written here in the title, A Long Journey to the Higgs, and also a little bit beyond. Fabiola will then cover all what concerns the Higgs and how we actually did make this discovery. So 20 years will be a theme in this talk a little bit. In fact, let me say that it was for me a pleasure to collaborate with Czech colleagues even longer than 20 years. But certainly in earnest on the Atlas project for 20 years. So I was also asked to maybe put a little bit the historical context to the Atlas and LHC project as a whole. And I usually start with this slide pointing out right from the beginning that the LHC project is really a global scientific adventure bringing together the accelerator, computing, and then, of course, the experiments. And this adventure already lasts more than 20 years. And it is really a great pleasure now to show some first results. Let's go back, and I would just like to say in two transparencies the main motivation, and maybe put the language, what we will talk about. Well, if you want, the main motivation in one slide is really to reproduce in a laboratory the conditions which were happening very, very shortly after the Big Bang, something like 10 to the minus 10, 10 to the minus 11 seconds after the Big Bang, when we consider proton-proton collisions in the LHC, maybe something like 10 to the minus 5, 6 seconds for the hadronization phase, which we also reproduce in the LHC when looking at heavy ion collisions. And just in one slide, this is the things we are talking about, namely the ingredients of the standard model, the three generations of matter particles, quarks and leptons, the force carriers, and then the question, why do these actually have a mass, in particular these heavy guys and other particles, namely the question of the Higgs field. So, how did really the LHC come about? Well, the first time it was mentioned something in 1977 when one was projecting for the next machine at CERN, which was at that time talking about the lab project. One was already saying this tunnel must be large enough to house maybe later on a hadron collider. Well, then in 81, lab was approved with this famous 27-kilometer tunnel, which we are all enjoying. And however, at that time, people were very skeptical, and it was really the early 80s, 83 typically, where one saw that actually hadron colliders can produce discovery physics. I'm showing here a very nice, essentially online display of a C into E plus E minus decay. This was part of the discovery of the Z bosons. And this, by the way, gave this very nice quote in 83 in the New York Times when it was saying, Europe 3, US not even Z0. 3, of course, because of the W plus, W minus. Now, you know the history. Then the US embarked into the SSC, which then was abandoned in 92, 93, whereas CERN and the community in Europe really started studying what machine one could really put afterlap into the 27-kilometer tunnel. So for the community, really, it started in '84 with the first workshop in Lausanne, which was organized by CERN and ECFA. Then there were several workshops, one very important in '87, which was the Long-Range Planning Committee of the Carlo Rubbia. And then there was a study in '89 in Barcelona where really the community came together and started building collaborations. And in fact, one of these proto-collaborations already included the Charles University and the group from the Academy of Science, the Physics Institute. And then Atlas officially was really born on the 1st of October, '92, so another 20 years to mark. And in fact, just a few weeks, few days ago, so to speak, we celebrated this. Fabiola Gianotti was presenting the collaboration, a nice birthday cake with 20 candles. So what happened on the CERN side? Well, in fact, '91 is another important date when the CERN Council made the statement that the Large Hadron Collider is really the right machine for the future of CERN. And then in '83, this a proposal was really put forward to Council, at that time talking about a startup date of 2002. And in '94, Council started approving, it took actually half a year, started approving the LHC first as a scaled-down machine because of resources. And then after a long effort to bring on board non-member states and to accumulate enough resources, finally at the December Council '97, the LHC, as we talk about it now and as we enjoy it now, was approved. This was done under the time of Chris Levlin-Smith as Director General of CERN. So the LHC, just again to put this into a context for the non-experts, Sergio has of course given much more details, but I just want to say that we needed, well, high energy, but also very intense machine because interesting processes like, for example, the Higgs, of which we will hear much more, in detectable final states happens only very, very rarely, 1 in 10 to the 13 or so. So clearly we needed very powerful detectors to find these very rare events out of these many collisions. So the experimental landscape, just again in 2 slides only, and then I come to Atlas, was we have 2 general purpose detectors, Atlas and CMS, and I mention here in interaction point 5, there is also the totem experiment, which we will hear more about later on today. There are 2 additional experiments, ALICE, and again we will hear more about that, and for heavy ion collisions in particular, and LHCb for B physics. And just a last colorful slides about the kind of kingdoms of the big collaborations, just to put you in context of some numbers. Typically 3,000 physicists. You also see the number of countries in the big experiments as well as in ALICE and LHCb. So let me now come to Atlas. Atlas is really a world-spanning collaboration, now with something like 176 institutions, where an institution sometimes is a whole collection of different universities. And I can say already here that Atlas enjoys really a long-standing and very fruitful partnership with the Czech groups since the very first days. Today, we have the Institute of Physics of the Academy, Charles University, the Technical University of Prague, and then the Palacký University of Olomouc in the collaboration. And just to give you a kind of a spectrum of the collaboration, as you can see, it's a very young collaboration. I always say if we would weight the age distribution with the productivity, this would even be a much bigger peak here. So Prague, in a way, played a very important role in the life of Atlas, because in 2003 we had a so-called overview week here. 2003 was just the year when the cavern was finished and we could start installing. So you can imagine that this was a very, very crucial milestone, and I have very nice memories of that time. This is the opening when the late Professor Niederle, who was always supporting so much all the CERN, Czech CERN efforts, and also, of course, the Atlas efforts, was opening the meeting. So Atlas is installed about 100 meters underground on the LHC at point 1. It's a huge detector. You can see it here overlaid with a 5-story building 40 at CERN. And just to give you a little hint about the technical complexity of the detector, I show you a short sequence of installing the huge supraconducting toroid magnet system in the cavern. This happened between 2004 and 2005. So this was the cavern empty, about 50 meters in the beam direction, about 35 to 40 meters in diameter, and one of the very big works, very impressive works over 1 year, was installing the toroid magnet, and this is a famous picture which you have certainly seen many times in the press. It's still shown sometimes in the context of LHC. Of course, we are not liking it so much because it's still empty. There are no detectors essentially there, except for a component where the Czech groups are very much involved, namely the calorimeter, and in particular the hadronic tile calorimeter. And so let me just say a few words about the Czech involvement. The Czech groups have been involved in this, what is shown here in green, the tile calorimeter. This is the most massive part of Atlas. You see here, for example, one of the end extended barrels on the surface built. It was, by the way, also led by Rupert as a project leader over 4 years in the early 2000s. A lot of construction have happened in many places, also here in Prague. We see here Michal Suk looking at a module during the construction in Prague. We see here also, for example, the Deputy Prime Minister inspecting the construction site, and this is a picture of bringing the bottom part of the barrel to the pit. This was in 2004. And finally, in 2006, this tile calorimeter was finally installed, and indeed it did fit. This was a very crucial moment in the construction. Now, the Czech groups are also have contributed very much on other parts of the detector, in particular very strongly on the tracking, both in the semiconductor detectors, both for the silicon strips and the pixels, again, also with involvement of Czech industry, which, for example, for pixel, half of the pixel sensors were built here in ON Semiconductor, former Tesla, and they got the award for excellent suppliers. This was the award ceremony. Again, we see here Professor Niederle. Another such award was, we were happy to give to Skoda Hutte. Skoda Hutte produced a massive but complex shielding part, which is shown here. This has been done under the responsibility of the technical university and was then produced and is a very visible and, of course, crucial component of the experiment. Somewhat more recent, since a few years, in fact, the Balaki University is working together also with other physicists from the other institutes on the forward detectors for Atlas. And I think it's fair to acknowledge here that, again, pieces, these Roman pots have been built, the mechanics in Czech industry, and we have profited a lot also from the pioneering work of the Totem colleagues in this particular case. So let me come back now to the experiment, and a bit chronologically, this was a great moment in November in 2009 when these people enjoyed the first LHC event, where we see here just tracks at injection energy, tracks in the silicon, just in the only in the SCT detectors, one of the parts where, as I said, the Czech groups were working on. So, Sergio has already given you a lot of history on the fantastic improvement, actually, on the machine in delivering luminosity. I can just show you that this was then, the machine was operating in 2010 for the first time at 7 TeV. This was the luminosity, which was surpassed by more than a factor of 100 in 2011. What this shows is always the accumulated luminosity in green delivered by the machine, in yellow what the experiment actually has accumulated. So this lot, you will see often both these luminosities about 40 inverse picobarns for some of the data. Already this gave a lot of physics. Of course, this even more. And the story is not finished because this year the machine is really working wonderfully. Let me also say that we have accumulated also in the Atlas experiment very efficiently heavy ion collisions, lead-lead collisions, for example, here at the end of 2011. Maybe another intermezzo of pictures. In the winter shutdown, just the last winter shutdown, we had the pleasure for a visit of the WT minister at that time, Ivan Wilhelm, who certainly is also a big supporter of the activities at CERN and a big supporter of the Atlas activities. So I will not talk about more about the machine. You got all the details. It works. These are the peak luminosities over this year, reaching very high values, as Sergio has discussed. And I can just say that today we have accumulated about 17 inverse femtobarn. So this is already more than a factor 3 compared to last year, delivered 18. And what counts very much and where an enormous amount of effort goes in is actually to assure the quality of the data. And you can see here, this is the quality of the different subsystems to actually deliver data which can be used for the physics. And what counts at the very end is really the efficiency for the physics, which is the efficiency of the data taking here, something like 94%, and another 94% typically from the data quality. So about 90% of what the machine delivers goes actually in the final physics plots. Sergio has shown you the challenges under which we operate, so I can just skip that. One of the big challenges and the constant work is really on the trigger to select out of these huge amount of collisions, several 100 million per second, the ones which you finally can store. This is done in Atlas in a 3-level system. We have typically something like, well, almost 600 different trigger items and make these many measurements simultaneously. They typically distribute in mainstreams, photon electrons, then jets missing ET and muons, each one about 100 hertz at the very end. And then others are, taken, for example, for B physics or hadronic physics. Some of them we cannot analyze because we will saturate the computing capabilities now, but we will have 2 years almost of shutdown where we will come back and analyze this data. Sergio has mentioned the computing, which is, of course, as I said, the third important ingredients for all this physics. I show this only to really point out that the large Atlas Prague Tier 2 works very efficiently and is one of the best ones of the about 50 Tier 2s we have in the experiment. So I will now come to some of the physics highlights, not talking about the Higgs, that comes later. And I can only say that obviously I have to make a very limited choice because we have, and this is true both for Atlas and CMS, published something like 200 papers already and maybe something like each one, and 400 conference notes which are also publicly available and they can all be found here on the web. And when I will show you a few physics examples, I will essentially go along this map of cross-sections. You see here many orders of magnitude. This is the total interaction cross-section, essentially, something almost like 100 millibarn. Then we have heavy iron B physics, few orders of magnitude below the standard model gauge and candles which we have, W, C's, tops, and then the interesting physics even much more below that. So just to say in one word, even the very ordinary collisions are very important to understand. And this is, I show this was the first Atlas paper essentially. It showed that, for example, the distribution of charged particles in the central part of the detector, or the PT distribution just of ordinary collisions, was not well described by the theory in the beginning, by the Monte Carlos. It needed, of course, tuning in order to understand them. And this is important to understand for all the background evaluations later on. The experiment is certainly capable of reconstructing particles which we know very well from the past. For example, cascade particle, or another example here is a BS decay. And one way maybe to show that the LHC experiments, CMS has a very similar nice plot, covers really a whole history of physics is, for example, just looking at muon pairs, where we find the discoveries from the past, J psi, upsilons, Z, and of course we are very interested what happens down here now. Let me say that in this spectroscopy, Atlas is proud that actually the first particle, new particle discovered at the LHC was not the Higgs, but was a chi b, some object of the order of 10 GeV or so in a spectroscopy evaluation, which involved quite sophisticated capabilities of the experiment. But what I want to talk about now are more the heavy particles, and I start with the standard model. Of course, the candles are really the Z in mu plus mu minus, or E plus E minus, and the W's in leptons and neutrino. And of course, to master this type of events is very important if we then want to look at missing energy in the context of supersymmetry. We have a huge number of events available to study already from the 2011 data set. Remind you, we have now more than 3 times more actually on tape. And just to show you the quality of the signals, these are E plus E minus events with the Z0 peak or mu plus mu minus events. Actually, these plots show you also the background, but on a linear scale you don't see it. You have to go to a logarithmic scale. So clean are the signals. And very similarly, we can see in the search for, in looking for W mu nu events, for example, just looking at the missing ET with muons above 25 GeV, you see a very nice Jacobian peak. And I just see Blada Simak coming in. We shared experiment in UA2 already, and we would have never have dreamed that at some point you would see these signals so clearly. I mean, it's a very nice thing. So, of course, these measurements of WZ allow us to test the standard model cross-section predictions and to have the first measurement now at high in the TV range. You can see that the agreements here is rather good. And you can go to much more detailed comparison of these cross-section measurements with predictions with different sets of structure functions and so on. For example, also testing universality and such things. Now, the Z is also a very important source to calibrate your experiment and to be sure that it performs as you would like it to perform. So this shows, for example, and notice the scale. This is 1 per mil. This shows you the energy scale over the run in 2011 from the Z0 measurement, or this shows you the energy scale as a function of the average pile-up events. And this is the only thing I want to show from heavy ions. We will hear much more about that and also why this is interesting. Atlas has, for example, also published the extraction of C peaks in this very, very busy environment of heavy ion collisions. I will not talk about the physics. That we may hear in the afternoon more about that. The next important thing which is being studied in the standard model is jet production. And this is an event where we have, for example, 2 jets of almost 2 TeV each one. Again, very spectacular signature. And this is kind of a collection of historical cross-section measurement. So I have shown you, we go up to, in the data now, up to even more than 2 TeV for the inclusive jets. this has been measured and was very important already in the 80s, in, for example, UA2, UA1 here. Then there were measurements at the Tevatron, and also in some special runs at lower energy on the LHC. And so you see here these cross sections. Now, this is just nicely to show the data. Of course, there are much more detailed comparison between the data and QCD calculations. Again, I just want to show you the flavor when making ratios up to very high dye-jet masses, in this case, in certain bins of pseudo-rapidity, we can then start distinguishing the performance of these QCD calculations and PDFs. Let me come to the highest mass particle which we know so far, which is the top. The top is a very important gauge because it involves really about everything you want to know from your detector to go for new physics. So leptons, because the top decays and the anti-top always essentially in a W and a B quark. The W can decay leptonically with a neutrino, so it is also missing ET, or it can decay in two jets, so you have jets, of course, and as I said, it's always top to WB, so you have B quarks, and B quarks give you displaced vertices. And just to show you one example of such an event, this is a particularly clean one, where both the W's decay leptonically, one in a muon, the other one into an electron, and if you zoom in, you see actually the displaced vertices of the two B jets. So if you ask these, for example, two tagged B jets, you see that you have very clean signal over the expected backgrounds, also in the ET miss plots. And again, this gives you the, you can use this then to measure the cross-section and compare here, for example, with QCD calculations, and actually these cross-sections have been combined in a joint effort together with CMS, and you see that really this cross-section measurement become very accurate and can be confronted with QCD calculations. And also single top have been measured. For example, here shows the single top cross sections at 7 and 8 TeV. Okay, the errors are still quite big, but we see the very expected behavior that you produce much more tops than anti-top because of the quark contents of the two colliding protons. So this is in itself a very interesting field, and I mentioned this, and of course then top properties can be studied and are studied, and some of the Czech groups, for example, are working on this field. So this is a summary of all standard model cross-sections which have been measured over many orders of magnitude. Similar results are available from CMS, and one can really say that the excellent performance on standard model processes make us really very positive about the ability of the experiment to look for new physics. Now, I was recently in China, and I was told that with the year of the dragon, we had in a very lucky year. This was in April, and I think this is really true, and you will see later on in Fabiola's talk about the Higgs. Just if I can have 5 minutes, 5 minutes, then a few remarks about searches beyond the standard model. And of course, such searches in particular there are many, many searches for supersymmetry. And the characteristics for supersymmetry is essentially that in the long decay chain, usually, which involves jets, can involve leptons, you have a lightest supersymmetric particle, neutralino here, which is stable and escapes detection. So it's a bit like the neutrino in the W leptonic decays. And basically, you look for configurations with all these particles plus missing transverse energy in some variables. For example, this effective mass, which is a strong component from the missing transverse energy, and you look for tails above the standard model background. And just one out of hundreds of such investigations, you look at these distributions, this effective mass here, in a region where you do not expect to have any supersymmetry contributions. The points and the understanding of the backgrounds is excellent. Then you are confident that you can look in phase space regions where you would actually expect some excess if there would be supersymmetry, and confront it again with the data. Well, you don't see any excess, so you can set upper limits on the cross-section. For example, here above this red arrows, and you can then confront these upper limits with model calculations from supersymmetry. And of course, if the supersymmetry model in question would have predicted a higher cross-section than what your limit is, you can say you exclude supersymmetry in that phase space. And that's exactly what one does. For example, here in a simplified model, these are some new data at 8 TeV. In a model where you can plot the squark masses versus the gluino masses, and everything below is excluded. So typically, in this particular simple model, squarks and gluinos up to about 1.4, 1.5 TeV are excluded. But there are many, this is just for the case where you have the largest cross-section. There are many theoretical arguments that maybe you have actually inverted hierarchy in a certain sense, and the third generations is the lightest supersymmetric particle. So you can, for example, look at TT bar squark, supersymmetric TT bar production is maybe the most important one, and you can see immediately, because the cross-section is lower, the limits are yet much lower. And again, the time does not permit to say much more about that than just to give you a list of searches for supersymmetry where you see that if squarks and gluinos are really the dominant, would be the low mass particles there, you can exclude it up to something like 1.5 or so TeV, but the limits are still much, much weaker for many other models which are maybe theoretically more motivated. So by far, the question of supersymmetry is not closed. Just one or two examples of searches for other exotic things beyond, I said. For example, you can look for heavy Z primes or heavy W primes, just doing the same type of analysis. Here we have the normal Z, the tail of the Z, and that is what we would expect if some hypothetical C prime, for example, of 2 TeV would exist. This is not supported by the data. Again, one translates this in upper limits for the cross-section, and one can then confront that with the predicted cross-sections, and of course at the point where the limit set by the experiment crosses the predicted cross-section for a given model, this sets us the limit, lower limit for the masses of such objects. And there are many, many such models. I, again, have no time to go into showing you several of them. Similar story, for example, to look for resonances in the case of photon-photon final state. So we're not looking at the Higgs. We will hear about that later on here at low mass, but again at the high mass tape. So unfortunately, time is too short, and I will skip the rest. Just tell you and refer to you that both Atlas and CMS, of course, are exploring many of these possibilities of new physics beyond the standard model. You see here a collection of lower limits for such objects, for example, leptoquarks, for excited fermions, and many other things. So let me stop by saying that really we have just started going into this new territory of TV range physics. We have started very well, as you will see, with the first discovery, but I'm sure there is still much more to come. And my last comment is once more that 20 years of working with the Czech colleagues and friends by now, of course, in Atlas was really a great pleasure. And we are looking forward for a bright common future with LHC and its upgrades, as Sergio has mentioned, well, for the next 20 years almost. Thank you.
Thank you very much, Peter, for your talk, and the questions, please.
Could you please estimate the full cost of the Atlas project, including the R&D and the operational cost up to now, and the manpower of institutes? And a related question, which subdetectors were mostly related by the budget?
No, well, the answer to the first question is this will be very hard. I can give you indication about the material cost of the detector. That is about 550 million Swiss francs, most of it in 1995 Swiss francs costing. So that's one aspect of it. Then the operation of the detector is typically, I give you a round number, about 20 million per year. That's the operation cost. Now, it's absolutely impossible to give you a number about the manpower costs in the institutes. This, of course, this would come to a very large number, so that I would not want to make even any estimate. I mean, it's clear that this is a big collaborative effort and relies on these essentially 200 universities and laboratories contributing. It's, however, I think the return is also fantastic with the physics and with the potential still to come. Okay. Now, you say, I have not fully understood the question about sub-detector. There are sub-detectors which, of course, are more expensive than others, but that's inherent by the nature. For example, the inner detector, the silicon detectors, that's certainly one of the most high-tech parts, which need radiation-hard electronics, and also so they are relatively expensive. There are other parts which were a bit less expensive. A big part of the cost also goes in the magnet system, because it's a huge magnet system, and that was certainly one of the bigger parts of costs in the subsystems.
Okay, thank you. So, some more questions, maybe from non-Atlas people? I could see one.
Please, can you tell about the plans, for instance, for leptoquarks or leptograms or something?
Well, let me go just back to this slide. I mean, we're looking indeed for leptoquarks of all the three generations. And where are we? At the moment here we have only put two, but we are also looking actually at the third generation. You see the current limits as they stand. This is certainly a field of big interest in the search for exotic physics. So, and this is a typical search which will profit very much from going to the full or near the full design energy. That's why I say we are only at the beginning. This is these data for the leptoquarks at 7 TeV still, and we will be running in a couple of years at 14 TeV essentially, and that of course increases the potential for higher mass searches very dramatically.
Okay, I think there is time maybe for the last question, for one more question. I couldn't see any, then let us thank Peter once again.